Okay, folks, let's go ahead and get going. All right. So, last time we left off on hydrogen bonds, and these are holding together most of the stuff that you probably care about the most. Things like any solution in water, of course, are hydrogen bonds. Most of the stuff dissolved in water, hydrogen bonding. And for example, protein, sugars, all of those are being held together by hydrogen bonding between the different molecules. This is going to be the second most powerful intermolecular force that we had covered. Does anybody remember the first most powerful intermolecular force we had covered? Ionic, you got it. Okay, so hydrogen bonds are actually fairly easy to figure out if it's a hydrogen bond or not. They have to have hydrogen. Number one, right? Hydrogen bond needs hydrogen. The second part is that the hydrogen has to be bonded to something extremely electronegative. For example, fluorine, oxygen, and nitrogen. So if you have hydrogen that's bonded to a fluorine, oxygen, or nitrogen, very likely it's capable of hydrogen bonding. There's a few cases where it would not be. For this level of chemistry, you probably aren't going to run into almost any of those cases. But like a quaternary amine is one of those cases. That's an amine with 4 things attached to it. Okay? It has a positive charge. It's ionic. So these, again, are always going to have what's referred to as a hydrogen bond donor and hydrogen bond acceptor. And what it is it's something very electronegative that has a lone pair that's going to overlap with that very positive hydrogen. Okay? And that creates a very strong magnetic attraction. You can think of them as really strong magnets that happen to snap together really well. Okay? Anybody ever had a stack of neodymium magnets? Or played with those? Neodymium magnets are the powerful magnets that you'd see on very high quality magnetic gear. No? Okay. They're so powerful, they're actually difficult to tear apart. Okay. Okay, I'll bring some in sometime, okay? Yeah, they're just very strong magnets, one of the stronger magnets you can get. Okay, so the last force here, this is the dispersion force. This force is actually essentially everywhere all the time, okay? If you have 2 atoms near each other, they're experiencing some level of dispersion forces. Now, typically, we don't talk about these forces where we have other forces that are more powerful. If you were tied down to your desk by a string or a piece of twine and a rope, which one would you be concerned about? The rope, right? How about a chain? The chain. So you always end up talking about the strongest force, don't you? In these cases, dispersion forces are like a piece of twine versus a piece of rope or chain. They're very, very weak individually. Okay? However, anybody ever seen that movie Gulliver's Travels or read the book? No? Oh, you guys are missing out. In that movie, they have Lilliputians, like 3-inch tall people, and Gulliver, a normally sized person, gets tied down with twine, hundreds and hundreds of pieces of twine. You've seen the, yeah. Yeah, it's a really good analogy, actually, for dispersion forces. So if you have one dispersion force, it's not a lot, right?
That's the one where when he travels from one land, he's seen as a giant in one. He gets thrown out, and then he's seen as like very small in the next one.
Yep,
Yeah, okay.
you got it. And it may be an allegory for him having delusions, and he gets put in the prison for delusions there.
Our test is next Wednesday,
It is.
and is that open enough?
Yes, it is.
And so it's just over everything for the last test now?
Yep, through chapter 7, which we haven't covered yet.
Like 1%?
No. Since the last exam. 5, 6, 7. Oh, no.
Will there be like a review on Pearson's again?
There will be. In fact, there already is. Yeah.
Are we finishing 7 today?
We won't finish it today. We'll finish it on Tuesday.
Okay.
Or Monday.
That chapter 7 is like due on Friday.
Oh, okay. Yeah, I need to move that. I need to shuffle it. Okay, so how do dispersion forces work? If you look at this room right now, did you guys distribute evenly across it? No, it has a bit of a buildup of people on certain sides, right? And so what we're seeing in this room is a semi-random distribution of people. If you all were charged, you would have one charge in one direction. There'd be a positive charge mostly up here, I guess. And there'd be a negative charge in the back, right? Okay. Whenever you throw things in the air, do they always land evenly around a central object? No, they scatter semi-randomly, right? And what that means is that many of the states and random states are not actually even, okay? Or another way of saying that is if you were to go to gamble, there's some people, less than half the population, that's wins-lose equally, okay? And then there's at least one person that has to have lost like 20 times in a row. And there's one person that has to have won 20 times in a row. Okay, and actually the one that they won a bunch of times in a row, that happened in Monaco, and it's very famous. They walked out of the casino with over $4 million. Yeah, but I actually have experienced the loss. I hate gambling. I have really bad luck.
Well, why are you gambling, dude?
I only gamble like I'll do $20, and only if I'm meeting people at a casino, just to, because we're at the casino, and it's weird not to do any gambling. But no, the penny slots are supposed to be a very, very gradual decline in your money. They're supposed to be lose a little, win a little, lose a little bit more, win a little, lose a little bit more than you won. And they're supposed to keep you playing. I literally am a 20 times, bing, 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 done. It's pretty funny, actually. It is actually quite amusing because like their algorithm isn't working properly. It's okay.
Do you need $20?
No, I'm good. I'm really bad luck, but I'm actually a really good investor. Yeah. Mm-hmm. Huh? 6. We're finishing up 6 right now. We're 8 slides from finishing 6. Okay, so dispersion forces are just the natural outcome from probability. Okay, when you have these electrons popping around that nucleus, there's actually more states in which they'll be uneven than they'll be even. And so what happens is one of these atoms ends up with the electrons gathering on one side, making it negative on that side. And it ends up with electrons not gathering on the other side, which makes it positive, right? When this happens near another atom, what's going to happen is that positive side is going to attract the electrons on the other atom. They're going to pull it towards it, okay? And what you end up getting is a very temporary state where the electrons are going to get pulled together in one direction. So you got a positive matching with a negative, and that pulls the things together, right? And then what's going to happen is the electrons here are going to repel each other because they're negative. This is going to happen there as well. And so they'll repel each other, and they'll end up shifting to the other side. And you get this temporary state where the negative charges oscillate together. And that'll keep pulling them together. Okay? Everybody good with that so far? Okay. Natural outcome of probability. Has to happen. Just like somebody has to roll like 20-something double sixes, and somebody had to have rolled 20-something double ones, right? Yeah. If you roll enough times, it'll happen. Okay. So melting points, how do these respond to real-world properties? So the melting points of substances are actually the strengths of their connections between the molecules or atoms. Okay? The stronger the connections or intermolecular forces, then the higher the melting points. Now, I had given you a relative strength of these so far. That was ionic, then hydrogen bonding, right? Dipole-dipole is next, then dispersion forces. Okay? Dispersion forces are typically going to happen where you have something like oil, okay? Gasoline. These are dispersion forces. Now, does anybody notice that there's oils that are like very, very high boiling points, very high melting points? Did anybody notice that before? Like Crisco, lard. Yeah. No? Okay, engine oil? No? Wow, okay.
It makes sense. I'm disappointed.
We need to like have a list of things you need to do in life. Like life experiences you need to have. All right. So, you are aware of gasoline though, right? Okay. Vaguely, and it evaporates fairly easily? Okay. 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 And you are aware that there is greases and oils that have that are solid at room temperature, right? That those exist? Okay. Fantastic. Then we're good. All right. So this is actually because these dispersion forces right here. So when you have gasoline, you have relatively short chains, relatively small things, and so you don't have a lot of dispersion forces that can happen near each other. When you get up into the very high boiling oils, the very high melting point oils, then you have much longer chains, and it has a lot more dispersion forces that can hold these together. You're just increasing the number of dispersion forces that can happen. Okay? Okay, now melting points and boiling points are going to probably be your two ones you know the best. When you have very high, very strong intermolecular forces, this is going to give you very high melting points and very high boiling points. Everybody's probably familiar with this in terms of salts, right? Which none of you have probably seen melted or boiled at all, because they don't melt or boil at any temperature that you're going to be reaching in your kitchen. Okay? Hydrogen bonds, you've actually boiled all those before. I know you have, because you've boiled water at some point in your life. Okay? All right. And that takes quite a bit of energy as compared to like gasoline, right? Which is boiling at room temperature usually. Okay? Or just a little bit above room temperature. All right. So here's some different examples of the different intermolecular forces. Here we have ionic bonds, hydrogen bonds, dipole-dipole attractions, and dispersion forces. And you can see the overall trend of these things in terms of melting point. All right, this right here is the comparison of bonding and attractive forces. So here we have bonds, covalent bonds and ionic bonds, and those are extremely strong, right? And then we have down here the connections between molecules. These are the intermolecular forces, and these are much weaker as compared to those, right? And we actually know this because when you boil water, does it turn into hydrogen and oxygen? No. Yeah, it's because the bonding is much stronger than the intermolecular forces holding it together. Okay? And so if it was the reverse, you'd actually turn it into hydrogen and oxygen first, then you'd boil. Which would be really bad because it would blow up. Okay? So, that actually is going to be very close to the end. We're going to do a learning check. We're going to ask you some questions. All right. So, we're going to identify, it'll come up again. We'll identify the main type of attractive forces that are present in liquids of the following compounds. So that's like ionic bonds, dipole-dipole, hydrogen bonds, or dispersion forces. The first one that's going to come up is actually going to be hydrogen bonds. Okay, everybody got something in their head for this? What are you looking for the connections for? Yeah. Yep. Okay, everybody ready for the code? Okay. Everybody ready? So hydrogen bonds. Ready, set, go. Which one could do hydrogen bonding? Okay, very good. Yep, water and NH3 or ammonia. Okay. Again, it's hydrogen is bonded to oxygen, nitrogen, and fluorine, right? There you go. Okay, so the next one is going to be the same list, and then we're going to be doing the so the NCl3. Those are the dipole-dipole forces. Does anybody have any questions why NCl3 is dipole-dipole? Okay, it has the CLs pointing down like that, and the CL has a significant difference between nitrogen and CL for the electronegativity. Okay, remember that when you have a dipole-dipole force, that means you have an overall dipole on the molecule. Okay, so it has a positive and negative end to it. The BR-BR, that doesn't have any overall bond dipole at all, does it? So we don't have anything else, so we just say dispersion forces. Okay? This right here, metal and a nonmetal, right? If it's a metal and nonmetal, it's going to be an ion. If it's an ion, then it likely has ionic forces, doesn't it? Okay. All right. Any questions? Okay, fantastic. All right, so that's chapter 6. Let's go and move on to 7. Dun, dun, dun.